we're going to do now is, now that we've looked at how cells are formed and how much energy they might produce, we're going to look at the applications of that in your life. So what are the applications of these electrochemical cells? Remembering that the chemical energy inside the cell is being converted to electrical energy, there are three types. We've got our non-rechargeable cells, we call those primary cells. They'd be things like you might find in a smoke alarm, a clock battery, your AA batteries. Rechargeable cells, so rechargeable batteries, you get those in your mobile phones and your laptops. So your lithium-ion cells would be rechargeable batteries, and fuel cells, which you might have heard of fuel cell cars. So we're going to look at each of those types one at a time. So non-rechargeable batteries. So they're designed to be used once only. The reactions cannot be reversed. That's the important thing, they cannot be reversed. So eventually the chemicals are used up and the EMF will fall to 0. So if we were to plot a graph for these of EMF over time, then they're just going to fall down to 0. EMF over time is just going to be steadily falling away. So these are the ones that are in our clock batteries, or our smoke detectors, your AA batteries. A lot of the batteries you buy in the supermarket are of this type. So here's a battery. You'll see that they're a little bit more complicated than the two beakers, because obviously we want to get them into as small a space as possible. This is an alkaline-based zinc manganese battery. These are the two half equations you're being given to you in the exam. For job number 1, pause the video, calculate the EMF. Remember, it's right-hand side minus left-hand side, which is biggest number minus smallest number. See if you can find the EMF. And you should have got 1.5 volts. Now it says write an equation for the overall reaction that occurs in the cell. When the cell discharged means when the battery is used. So when the battery is used, the most positive one gets to go the way it's written. The negative one, we're going to have to turn it round, so you might need to rewrite that the other way around. And you need to make the electrons match. So at the moment there's 1 electron in the top and 2 in the bottom. So I'm going to double everything in this top equation, so that there's 2 in each. And then I'm going to combine those, remembering that the bottom one needs to be reversed. So 2 MnO2 and 2 waters. The electrons are going to cancel out, react with zinc to make 2 MnOOH plus 2 OH minus plus Zn2 plus. Yeah, so that is what is happening when the battery is working. Now it says decide what you think the function of the porous separator is. Now let's have a look at our battery. Remember, when you put this battery into your clock, that your wires are going to sort of connect from there to there. Yeah? From the negative to the positive terminal, electrons are going to flow from the negative to the positive. So these two bits of metal, or in this case we've got one that's carbon because we know that graphite conducts, these are our electrodes. So that's where electrons flow from. What do you think the porous separator is? So on the outside we've got a zinc and zinc 2 plus. So remember that this is just Zn and this is just Zn2 plus. So we've got Zn on the very outside, then Zn2 plus next to that. Then we've got our porous separator, and we've got the MnO2 paste, which contains all the things in that top half equation, and then we've got a carbon rod. So what's the function of the porous separator? Well, the porous separator is the equivalent of the salt bridge. It's going to allow ions to flow from one half cell, from the zinc half cell to the manganese half cell. And the function of the carbon rod is it's an electrode, so it goes to allow electrons to flow into our circuit. Now the zinc electrode is also the container of the cell. Suggests why the cell might leak after a long period of time. So if you've ever seen a battery and then it's gone a bit crusty around the edges, what's that about? So look at your overall equation, what's happening to the zinc in the reaction as it's being used up? So the Zn is oxidised, so it's going, and so it won't be there at the end.